Good morning, everyone, for today's distinguished webinar series in AI and cybersecurity as part of Center for Cybersecurity Research at the University of North Dakota. Today's distinguished speaker is Dr. Kevin Jin, Associate Professor, Department of Electrical Engineering and Computer Science from University of Arkansas. The title for today's talk is Enabling Programmable In-Network Security for an Attack-Resilient Microgrid. Dr. Jin is an associate professor, as I mentioned already. He earned his Ph.D. in electrical computer engineering from University of Illinois at Urbana-Champaign. His research focuses on cybersecurity, networking, cyber-physical systems, security, and resilience, as well as the modeling and simulation of large-scale systems. Dr. Jin and his team have received 5 Best Paper Awards from many conferences, such as IEEE SmartGridComm, IET Cyber-Physical Systems, Theory and Applications, and ACM SIGSIM PADS. He currently serves as an associate editor for ACM Transactions on modeling and computer simulation, and as a member of steering committee for ACM SIGSIM PADS. He also created the CS Master of Cybersecurity program at the Illinois Institute of Technology, where he served as a founding program director. Dr. Jin is a recipient of the Air Force Office of Scientific Research Young Investigator Program Award. Dr. Jin, thank you so much. It's a great honor to have you as part of the webinar series at UND. Thank you again for your time this morning, and the floor is yours.
Okay, yeah. Thank you so much, Prakash, for the nice introduction. And everyone, it's really my honor to be here to talk about cybersecurity, particularly in smart grid in industrial control systems. So, first of all, I'm wondering, let me share my screen. Let's see. Okay. Can you see my screen?
Yes.
Okay.
We are good. Yeah.
Okay, thanks. So today I'm going to speak about cybersecurity in industrial control systems, and in particular in the context of smart power grid, centered around a novel software-defined networking-based framework. So let's see. Let's move forward. Before I talk, I would like to thank all my students, all the team members for their so as a faculty member. It's always I'm always thankful to working with a team of great students. That's probably the best part of becoming a faculty member. And also, I want to thank to our sponsors and the industry collaborators, so that without them, their generous support to make our research project happen smooth. So our current research interest is in the cybersecurity, computer networks, and simulation modeling for large-scale systems, in particular with the application of smart grid. So in today's talk, I'm going to show some of our works in this topic. So today's quality of life is highly dependent on the successful operations of many large-scale industrial control systems, because they control lots of critical infrastructure such as power grid, transportations, oil and gas, wastewater treatment. So in order to increase the efficiency of those control systems, so modern ICS, we have seen that they increasingly increase the adopting the internet technologies into the communication infrastructure. For example, the smart grid has connected various type of networks together, such as like smart meter networks, the AMI networks, or the phasor measurement unit, PMU networks for wide area monitoring. So before I proceed, I'm wondering, is the voice okay? Is the sound okay? The volume okay with the audience? Or should I speak louder?
It's good.
Okay. So I borrowed this picture from NIST, and this is a big overall picture about smart grid. So as for now, we can ignore the details and focus that. So this is no longer a physically isolated system, and smart grid nowadays become a complex network of networks. So the interconnectivities actually opens many paths for malicious users or attackers to access those critical control process and the informations which they used to which they couldn't do in the past. So on the one side, we have efficiency because of the new technologies. On the other side, we have to keep in mind that they are critical infrastructure. So the impact of attack is no longer on the cyber side. They have the physical impact. So we should always ask, what is a security, like what is the security impact before we apply any new technologies? And how can we verify the impact? So this worry is not in theory, and we have seen many real examples on how attackers happens in energy systems. So such as some malwares like Stuxnet, Dragonfly, Shamoon, and we have all seen this happens in real. So in order to protect the industrial control systems, so typically the utility use commercial off-the-shelf product, such as applying firewall, anti-spyware, antivirus softwares onto those end hosts or the network. So for example, if you consider firewall, and firewall can be good only if that we configure things correctly, but they can only protect a single device in a local view. But if we consider many firewalls that exist in the big network, there might be global conflict. Although individual one looks good, but there will be global conflict. So this will be caused by misconfigurations or sometimes cyber attacks. So we need a way to check the system-wide requirement, such as security, such as the performance, like end-to-end delay. On the other side, we should also say, because this is anywhere critical infrastructure, so how can we integrate the existing technologies to them is challenging because we do not want to affect real-time operations, and we do not want interference with those normal operations. So the current testbed, the current systems, testing on that is not a good idea. So we should always testing on a testbed before we apply that into the real system. But lacking a high fidelity, scalable testbed is another interesting research challenges that we need to address. So in our work, we focus on integrating the novel programmable networks, in particularly software-defined networking, SDN, or its extension like P4 into the ICS to enhance cybersecurity and resilience. So our work has like 3 contributions. So first of all, we integrate the SDN-based architecture into the communication networks of the power grid, so that we have control and programmabilities into the existing communication networks. The second, based on this infrastructure, we developed a couple of security and resilience applications, such as real-time verifications, such as self-healing management, such as intrusion detections on top of those SDN-based architecture. Third, we also develop a testbed that utilize the parallel simulation, which for scalability, and also the virtual machine-based emulation, that is for running the real code in the containers for fidelity. So we combine those 2 techniques together to form a hybrid high fidelity testbed for smart grid. And that's, of course, integrates software-defined networking in the testbed. So in the remainder of the talk, I'm going to quickly go through the background of SDN, then introduce 2 applications that we are used based on, that we explored based on SDN infrastructure. And if time permits, only if time permits, I'm going to look at some testing and evaluation platforms. So that's the plan for the talk. So first of all, the SDN background. So what's the SDN and why SDN, right? So in today's network, when we consider the core of the network, not any device, the core of the network, where the packet was being routed or switched between multiple hubs within the network. So if you think about the core of the network, so this is how the system looks like. We have specialized hardware. On top of that, we have specialized applications and a control plane. So only a vendor like Cisco or Juniper knows how stuff work. And we as a user, we have no idea how those boxes work within our network. So if we need a new feature, we can either contact Cisco and Juniper and have them developed in a much longer time, or maybe the time that is developed is no longer useful. So that closed environment actually slow down the innovation. So what we, so that's slow down the innovation. So what we intended to do for SDN is that we want to open up the interface for the networking so that everyone else can develop like your own applications on top of the network. So in order to achieve that, so we need to develop a unified control plane that interference between the underlying networking devices and the layer application. So on top of the control plane, that a user can develop their own applications. So all these are based on the open interface. And thanks for the networking community that this idea is being developed and realized through SDN. So what is SDN? SDN is basically a way that if you think about OS, operating system, that OS actually shielding us from lots of details how to interact with the underlying hardware that a user like you and me, we can develop applications on top of that. So we're trying to have the same idea applied to the computer networks, and so that the networks now become a network OS, and users can develop their own applications such as like access control, such as intrusion detection systems, such as different routing algorithms on top of the control plane, and that's user-defined application based on a unified control plane. So this is the idea of SDN. So if we bring that into the SDN architecture, so it has 3 layers. So the lower layer is called a data plane. That is how the packet is being moved, physically moved from one place or one input port to the output port. Then we have the control plane, where is a piece of software defined by and developed by the community, and we can use that to provide things like now you have a centralized control, centralized view of the entire networks. So we also have the global view of the entire networks and centralized control, and also allows us to directly program the networks. So some of applications later you're going to see, like a network verifier, is utilize all those 3 features to efficiently verify the networks. So this is the basic 3 architectures for SDN network. Okay, so now let's look at the first application that is based on SDN. We are using that for network verification. So researchers have performed some survey with the network operator, who's supposed to be the ones that is the most familiar with the networking configuration and operation. However, many of them still feel that they are not sure whether their configure is okay, is good, or any change may cause problems. Excuse me. So the underlying reason is that nowadays our computer networks become more and more complicated. So there's multiple users, many applications running simultaneously on the networks, and they may conflict with each other in terms of the objective. So it's very hard to define what is the correct behavior, even from the operator's perspective. So if we apply that to industrial control networks, that also will give the undesired impacts, such as unauthorized access to certain resources that you shouldn't have access to, and make certain critical services unavailable, or the physical impact will be cause instabilities or loss of load synchronization issues within the physical power grid. So what is network verification? Network verification is that if I have a view of the networks, so on the one side, I have a view or have a model of the networks. On the other side, I have some policy that one need to enforce for your network. So for example, like if A want to access B, then A can only access B through firewall. So we want to make sure that all the paths leading from A to B must go through the firewall for checking. So there is no actual path between A and B that can bypass the firewall. So this is one rule. So there can be other rules, like if A want to talk to B and the communication cannot have black hole, or there should be loop freedom within the communication path. So you can define the the policies, and we have the model, and we need to verify that if this policy holds at any instance of time. So in the past, what people did is that people developed tools for verify the network snapshot based on the static view. Then then the next one is that, okay, because network keeps evolving, and the dynamic verification is needed in addition to the static one, because the network keeps changing, the rule change, the people join and the left. So people develop other tools to verify efficiently about the networks in a dynamic on the fly way. However, none of those works consider a thing called timing uncertainty, which means that at some time whether your rule hold or not, it depends on whether your rule is always hold true or not. Maybe at the beginning it's hold true, at the end it's hold true, but during the process of the conversion, it may or may not hold true. So that's a thing called timing uncertainty. So I'm using a quick example to illustrate what is timing uncertainty. So let's see, we have a simple network with switch A, switch B, and a controller. So right now, we have a simple rule saying that all the packets from switch A to switch B will always go to switch A to switch B. So all packets from A to B. So that is our current rule. So now I want to have a new configuration to make the flow in opposite way. So rather than A to B, now I want to things from B to A. So what you can do is that the controller send a rule to switch A, say remove the rule 1, and then install another rule onto that. Say I install another rule on the switch B, so that now I have a new rule. So once you issue these two rules, remove and add a new rule, the configuration is being configured. However, in the networks, the actual thing is that because the network is full of uncertainty, for example, queuing delays, congestions, so the first rule may be delayed. And when the controller issued the second rule arrived at switch B earlier. So now we have a new rule that while the rule 2 has been applied, the rule 1 still exists. So there's a timing window that we have a temporary loop in the network. And if your policy is that I have to have a loop freedom policy, then during this time, during the transition time, your system is temporarily violating the rule, violating policy. So the underlying reason is that the controller think there is only one option after I issue these two rules. There's only one deterministic way of the networks. But in reality, because of the delay, you can be in any possible of the one of the 4 possible states after issue the two rules. And the controller have no idea which of state the network is at after the rule is issued. So in order to present these possible ways, So if we want to present all the possible ways for verification, then then that's going to be very we're going to have lots of states, basically 2 to the power of n states. N stands for the number of possible change. Then so that's going to be too much. So one way we making our networks we compact of network models is that we develop a thing called uncertainty aware graph, where we use a like solid line to represent a certain path, and dotted line represents an uncertain path. And the uncertain path can change to a certain path once the acknowledgement from the other end is received, or after its certain time has been passed and no alert is being raised. So we're using the uncertainty graph to represent all the possible network states in order to save the number of states. So based on the uncertainty graph and SDN networks, then we developed a verification system. So there are 3 steps of doing that. So one is so the system takes a stream of dynamic updates, and when updates comes to the verification, it verifies each updates against certain system policy before we apply the updates to the network. So the verification actually consists of 3 steps. So in the first step, we reduce the whole search space by generating the minimum affected network models. So we're not actually performing the verification on the entire models, which is too much. We look at how does this update, what portion of the network will be affected by this update. And then we only extract the part of the network that will be affected and form a reduced search space of the network. So this is the key step to achieve the real-time performance. And then we generate so-called uncertainty-aware graph model based on the reduced models of the network. So finally, once we have those uncertainty graph, we know the paths, we know how they are interconnected, then we perform the traverse of the graph model to verify that whether a policy has been held true or not. So this is our 4 steps. So in the paper, we also have more details like how can we enforce how do we perform things in a parallel way so that we can achieve the maximum parallelisms and increase performance. So for example, in this case, we have in our system, we have the orange color is the older rule. So A reach B through C, D, and E. And our new rule is that we want to change that to A, F, G, H, B. So eventually, basically, we want to flip the top path to the lower path. So I want to make sure that during the transition between A and B, nothing is wrong. All the policy has been still hold true. So so one way we can do that is we can issue 4 rules, and for each rule comes into the networks, we verify it, and before we apply that, we verify the models to see that if the path is hold true. The policy is that at any instance of time, there's always a path from A to B. So in this case, if we issue the rule that remove A to C, that from A to C to A to F, so that so this rule cannot be done at first. So what we will do is that we're going to buffer that rule and apply other rule first before we apply this rule. So so our verification systems will check this rule one by one and decide whether we buffer it or apply that and when to apply that. So this is a simple example. However, the design is straightforward, is fast. However, as I talk for now, if you follow these ideas, and you may think that there might be a problem with this approach, because the system may encounter deadlock. The reason is that A depends on B, B depends on C, C may come back depends on A, right? So there's an interdependency, and they may form a loop and cause the system to become a deadlock. So in order to so the key problem for the key objective for this approach is that we want to achieve the verification in a real time, in a very fast way. So what we did to address this design is, first of all, we prove that there's a type of class of network which is called segmentation-free networks. They will never have deadlock. So there's a class of networks that this algorithm always work, and they actually contribute a great amount of networks. And then we run lots of experiment in with the data and the topology of the real networks, and we find that okay, in reality, it happens, but happens very infrequent. And the last thought is that if we do have a deadlock, our solution is that we will fall back to a more heavy-weighted solution that is being proposed and studied at Princeton from the SIGSIM paper. So this is our approach. So our approach is lightweight, but if there's deadlock, we can always fall back to a more heavy-weighted solution. So we utilize some like a real network, a real campus network topology with 200 devices, layer 3 devices, and perform some real tasks. So we divide those snapshots into all data into 24 snapshot, and each for like 1 hour transition. And we know that in the baseline, we call immediate updates. The idea is that whenever there's a incoming updates, we just apply that immediately without any verification. Verify that before application. And the consistent update is the truth from the Princeton University, marked in blue. So we can see that in most of the case, our system, in terms of the speed, in terms of the memory usage, in terms of number of rules, is always close to the immediate updates, and saves lots of memory from the compared with consistent update. So both space and the time is better than consistent updates. During the time between 11 o'clock to 1 o'clock, we see that the network has lots of change, and there's about 8,000 updates during those 2-hour windows, maybe because of the network is undergoing a maintenance. Then we see that the performance is still good in the sense that it's closer to the immediate updates. We saw that there's among the 8,000, 10 times it's fallback to the consistent updates. But still, in terms of the memory, it's kind of saving maybe half of the memory compared with the network consistent approach. So overall, this approach is lightweight, achieve real-time performance, and also consider the time uncertainties that none of the previous work considered. Okay, so now I'm going to talk about the second application. Also based on the software-defined networking. So it's about software-defined network. It's about PMU networks for phasor measurement unit. So phasor measurement unit, PMU, is a application that has been growingly used for wide area networking, wide area measurement and control system. So it was deployed on the transmission systems, but nowadays we even see micro PMU being deployed on the distribution system. So the benefit of PMU is that it provides lots of data compared with the traditional SCADA system, and all data are time synchronized through GPS. On the other side, while PMU is useful, provide fine-grained data, lots of data, but on the other side, there's also challenges. The particular challenges that we are focusing here is the cyber attacks and the human mistakes. And we have seen examples how the PMU system can be attacked by denial of service attack or man-in-the-middle attacks in the past. So for example, if we have PDC, PD stands for phasor data concentrator, is the concentrator of the data. So PMU collects data and sending to PDC, and PDC sending to the control center. It's organized in a hierarchical way. So when the PDC or PMU are under attack, so especially as the PDC is in attack, and then all the data may be either compromised or false data, or they shall be wrong data that be collected by the control center. So the consequence is that the observability of the system is being largely impacted, and this will affect certain critical applications such as data estimation in the control center. So we want to address this. So our objective is that can we utilize SDN to design a self-healing PMU networks? So our objective is that we want to recover the system observability. Meanwhile, so in terms of so when there's attack, when there's a compromised devices, when the compromised devices is being detected, we want to isolate those devices and then reconnect those traffic from the uncompromised devices, uncompromised PMUs. And the objective is that we are not only considering the network recovery, but also recover the system observability from a power system perspective. And the speed needs to be fast, and all the process needs to be easy to deploy and at a low cost. So we utilize SDN, and because SDN knows and we also utilize the global optimization because SDN has the global view of the network. And we also design a prototype systems to for evaluation and the testing purpose. So I'm going to present this idea using an example to better illustrate what we're doing here. So let's say we have a phasor measurement network with 2 PDC and 3 PMU, and they're connected through a couple of routers. So the PMU measures the power system status, and then they collect data and transmit to PDC. Then PDC go to control center. So first of all, we set up a network layer between the PDC and the PMU using SDN, and assume that PDC and PMU all connect using IP-based network, and then we deploy SDN on top of the control on top of that, which can see the global view of the communication networks. So we set up such network in Mininet, and then our system models for both power system and communication system are based on graph. And we have 2 graphs, one for power, one for the communication networks. And then we set up a PDC and the PMU models using a simulation softwares and running that on Mininet. So now the PMU can report measurement to PDC control centers, as we see here using the green arrows. So PMU reports data to PDC, and they're running both simulation softwares. So meanwhile, we also define what is the so-called power system observability function. So that is based on 3 facts. One is if this PMU can observe the current bus that I'm sitting on, or I can observe the immediate neighboring bus, or if I have a loop and a certain measurement unknown, I can quickly calculate the rest bus by using a zero injection bus. So there are 3 ways we define the observability. If system is observable, that's 1, following these 3 categories. Otherwise, it's 0. So we are replacing, like we are injecting the real data collected from the Illinois Institute of Technology's campus PMU network, and then we replace those data in our system. And we can see that for the PMU1 and PMU3, they're monitoring like the status of the power system, and that is what is showing on their interface. And then, so that is a normal condition. So if everything works correctly, the control center is able to see PMU1 and PMU3 in real time. And then we are running a attacker tool that sending lots of denial of service attack to render one PDC, in this case PDC3, useless. And we can see that PMU3, the data will disappear, and PMU1, the data still exists because PMU1 is still available, but PMU3 is being attacked. So in order to self-heal such network, so our algorithms basically will form a optimization algorithms using two stages. So the first stage is that we identify a set of PMUs that needs to be restored. Consider that there's a redundancy in the network. We don't have to restore all the PMUs at one time because if our goal is to maintain the full system observability and we want to do this as soon as possible, then we don't have to restore all the PMUs. So we select a set of PMUs or maybe a subset of PMUs to be restored. And second is that we want to define how many of the rules, we want to minimize the number of rules to be installed in the network so that we can minimize installation time. So the formulation is also have some constraints, such as one PDC can connect only this much of PMUs, and we want that the bandwidth between any connections, they are still over provisioned. And also there's a limit about how many rules can be installed on each PMU, on each SDN switches. So these are the constraints we perform before we run while we're running this optimization. So we're running these optimizations in the controllers of SDN using our own applications, stage 1, stage 2, and then we get the set of shortest paths. The shortest paths will be installed through the direct programmability of SDN, install that onto the network, onto network devices, so that the packets will follow the right path to self-heal the network. So as a result, we can see that now the new path is being created, and as shown in the blue color shows the new path is being created. And then as a result that now both PMU3 and PMU1s, their status are being restored and can be seen by the control center. So we restored system observability. So this is a simple illustrative example, and we have done extensive evaluation for the system for evaluation on the systems for like the IEEE 30 bus and IEEE 118 bus. So the system has been developed in Mininet, that is a container-based SDN emulator, and we look at metrics such as observability, recover time at different stage, and we also develop a rule compression module that to compress the rule so that maximize installation time. Minimize installation time by minimizing the number of rules to be installed. So the figure here shows that with the self-healing scheme, compared with other self-healing schemes, that is our system observability can always be remained at 100%, while if we don't apply that, it will be dropped. It will be dropped significantly after certain PMU PDC has been compromised. Okay, so that's the second applications that I can talk to. So due to the time constraint, so I may not be able to have enough time to talk about the test bed. So I want to leave enough time for question and answer. So I will very quickly go through the test bed. So we design test bed. So one way you can do test bed is we can do real test bed. However, the real test bed is not always easy to configure because inflexibility is not to reproduce anything. So in order to achieve the scalable test bed, scalable testing, we need to create our own test bed. So our approach is that let's use simulation and emulation together. So here's the design of our test bed, that we have 3 layers. Underlying is the software-defined network emulation, where we run virtual machines, and the virtual machine in terms of the container, so that we can run an unmodified code. For example, if you have AMI networks or PMU networks, you can run the emulator. You can run the software immediately rather than having your own models of the PMU or AMI. So, and on top of that, we have a parallel simulation, which is mainly for scalability purpose. And then on top of that, we have network simulator, and also the power simulator. And in our case, we're using OpenDSS as power simulator and S3F as the network simulator. So this work has been applied in IBM and Boeing for their Argonne National Lab for their research. So I'm going to quickly go through that, and then maybe just go to that. Okay. So let's talk about the some of our ongoing work and the future works regarding how to apply programmable networks into the smart grid security and the resilience problem. University of Arkansas is have a couple of centers related to smart grid, and there's one center for smart grid security, and also we have a large facility for testing purpose. In our own security testbed, we have devices from SEL, devices from Typhoon, from OPRT, and all the from anything from like generation, transmission, distribution for testing purpose. On the other side, we have other technologies like high performance computing centers. So, but the problem is that these are devices that is being brought for different topics, for different projects. So it's like you have a big house, and every time you do some renovations, you're adding some new equipment for different projects. So the idea is that they are dedicated equipment for different projects, and can we make use of all of them for having a test bed that we can run more complicated and high fidelity testing. So the idea behind that is we want to design a virtual test bed that integrates both the real devices and the virtual devices through emulation and simulation technologies. So the idea for that is we have power system, real systems, real equipments, virtual equipments, simulators. We have networking, communication network equipments, emulators, systems, and we want to create a platform that they can all talk together. So one challenging things about combining them together is the time synchronization. So because different devices, different systems are talking advances and speak in their own clock. So how can we synchronize the time between all of them, so serve as a basis for advancing things in a meaningful manner is a challenging problem. So we have a solution, and we are still working on the solution. It's improving the solution. Our solution is that, let's say we have a test bed, and so the test bed including a thing called a virtual time. So rather than having the simulator to catch up the real time, which is sometimes harder because if a simulation is running lots of workload, then it's hard for you to run real-time simulation. So rather than having the simulator to catch up the real time, our idea is that we can embed the virtual time onto the real devices. So essentially what we did here is we developing a kernel that, a Linux kernel that we embedded virtual time into Linux kernel. So any containers and virtual machines that are running on top of that kernel will have its own notion of the virtual time. So, for example, if a process is in the idle state, or is in the is in idle state, it will not advance its clock, while the other process may advance, but that particular containers will not advance its clock. But before that, everything will advance, no matter whether you are in a wait state, idle state, or processing state. Right? So this way, we have things called temporal fidelity to ensure that, and those virtual time will serve as the basis to synchronize among simulation and the real software. So that is one direction to have this overall test bed. So the other direction that we are currently working on is moving the programmability from software-defined networking from the control plane to the data plane. So we're exploring things called P4. So P4 is extension of SDN. SDN have controllabilities on the control plane, where the switches have less programmability, where the P4 that it has a P4 language that you can actually inspect all the packets going through the P4 switch, and then look at the content of the packets, and can also modify the content of the packets in real time, so that so you can do lots of more customizable programmability within the data plane on the devices. So by doing that, lots of our existing solutions can be migrated from the centralized control to the distributed control, and it's from the solution rather than happen on the control center in the last stage. Now our solution can be happen within the network while the packet is being transmitting. So for example, if I have a detection engine, so rather than you wait until the last end to detect malicious activity, now I can monitoring and mitigating attacks upon detection within the network while the traffic is through in the intermediate network devices. And also we are looking at some AI technologies being deployed on the controller of the switch and also on the data plane of the switch. So these are some works we are currently investigating. So to conclude, so our goal is to build a secure, resilient, and safe cyber environment, particularly communication networks for industrial control systems that operates many critical infrastructure. So we utilize SmartGrid as an example, and we do explore multiple applications such as PMU, such as AMI within the network. So we also develop a testbed that utilizing parallel simulation and the virtual machine emulation for scalability and fidelity. So that concludes my talk, and I'm happy to answer questions. I think that's it. So I think I passed the test that Prakash gave me 45 minutes.
Fantastic. I think thank you so much for sharing your insight on your topic. So let's see if we have some Q&A. Maybe I'll start with a couple of questions. First question is, you talked about this self-healing scheme and for the PMU application. Other than system observability and recovery time, are you looking at other metrics to for evaluation?
Okay. Yeah. So I think that's a good question, especially from a domain expert. So in traditionally, if you talk about communication network, communication network people will cares about what is the recovery speed and how much changes you needed to reform the network, and what's the speed. If you talk about to a power system people, then people talk about availability, like situational awareness, observabilities. So our idea is that we want to combine things together. And there's some common metrics that both parties are interested in. So most the common interest, the matrix that both parties are interested in is the recovery speed. And that is actually a very complicated matrix that we want to, if we want to consider timing, is very, very complicated. So because of timing, including processing time, propagation delay, queuing delay, which is the very, very hard to model, and then also the processing delay within the device and within end host. So that would turn out to be a very complicated problem. So in this work, we actually simplify that. Rather than looking for continuous value, we are looking that into discrete value. That is, we kind of migrate that into the number of rules you have to install. So if you think further, the number of rules, the smaller the number of rules installed may not reflect may not exact means the smaller, the shorter recovery time. But there's some positive correlations, but it's not exactly the same. But we choose that because it's easy to form our algorithms. Otherwise, if I'm running too long for the optimization, we couldn't declare real time. So on the other side, the recovery timing is very, very complicated. So another thought for that is if we can transfer that into like a bandwidth, whether say I have this many bandwidths, if every time it comes in a new change, you make sure that you not exceed the maximum bandwidth so that you won't exceed the extra queuing delay. So that's something we can do. But as long as we consider queuing delay, things will become very, very complicated.
Super. Thank you, Dr. Kevin. I think I asked a question because when we talk about resiliency, and then, and then now that you're moving from control to data plane and looking at this programmable data plane. So I was wondering, that's why I was just trying to see, how resiliency definition is going to change or the metrics is going to change. And but it's interesting. But thank you for giving me some perspective. And on that P4 concept, is that something that you guys are coming up with, or something that you're referring to some federal regulations that you're following, or is it? Help me.
Yeah, I wish I could come up with that idea. That would be a fantastic idea. So no, it's not coming from us. It's coming from the networking community.
Sure.
I view that as an extension of SDN. So these days, if you look at like top networking conference or top security conference, you can always find like papers, every papers like over the past 5 years, you can always find papers on this topic. So the idea for that is you're migrating the programmability from the controller, centralized controller, to the decentralized switch. And the switch itself become more and more powerful because the processors that you developed on those switches, they are specialized processors, and they can handle network traffic much faster, maybe 100 times 1,000 times faster than CPU. So they're designed specialized for processing network packets. So, and now we're allowed to program that, and we can define our own customer headers. We can look at the data, so we can do some simple operations, and then create our own customer headers, and then adding data that we collected into the header and pass that to the next P4 and toward the end host. So these are something that is being currently pretty popular in the networking community, and we're utilizing that in the smart grid.
Super, thank you. And you have a fantastic test bed that has so much of interesting elements and components. I think that's is your test bed is actually accessible to others? Or are you at a project by project, case by case? Is it actually not yet made available open source for people to use? You talk about, I attended an SF-CPS meeting, and when they talk about test bed, I think the test bed should be as long as people users use from elsewhere, then you can call it a test bed. But at the same time, how do we make sure that we design some test bed that that has a seamlessly integrated for external participants to access? So
okay. Yeah, so I think that's another good question. So let's say so long story short is that all those fantastic projects, they're not just by myself. I mean, it's coming from a group of people that at University of Arkansas, particularly led by Dr. Alan Mentus, and also Dr. Chris Farnell, which is a collaborator that we had in our ICAI center. So it's coming from different projects, but to answer your questions, so there's two types of testbed. So one type of testbed is connecting to like more like power system testbed, and that is open to public, and you have to pay to get things tested. So on the other side, we have a so-called a cyber testbed that is linked to like ICS systems such as DMP3, Modbus protocols with those devices, and with like Typhoon and OPRT, those are accessible. So we call this cybersecurity testbed, where we have both virtual part, which different software, probably that vSphere, like NetLab, and different kinds of virtual machines running host, and combine that with SEO devices. So in addition to that, so why we want to make this open accessible, other than the research purpose, we also have some workforce development task we are performing here. So one thing we are using, let's say SDN or P4, we are collaborating with I think South Carolina University. I mean, they have a very nice NSF funding with modules for net labs, and within the net labs, they have modules like introduction to P4, introduction to P4 application development, introduction to SDN. So those are the modules that we are using, and we are developing our own modules based on that for ICS security that is open to hopefully open to public soon, and so that people can use those platforms to kind of build, like creating virtual machines and testing connection between them to experience the security of ICS.
Super. Thank you. The question of, I'm building a small test bed here and on edge computing with cloud, and I was wondering whether how we can collaborate and maybe talk to your test bed, and somehow we can, do some kind of ways to interchange some analysis. But that's great. Let's see what else the questions here. What software technology used to create SDN? This is the question coming from.
Okay, let me look at chat. So let me unshare the window and let's look at the chat. So where's the chat? Oh, the chat is here. Okay. Let me unshare the windows. And what?
Okay, I think the second question is probably just how did you create this SDN environment? I'm assuming you said you have some containers, or you
Sure.
relying on some kind of cloud and a combination of or Docker.
So there are two ways that we can do a test. So the easier and handy way of doing that is using a thing called a Mininet. And a Mininet is a container-based emulator. So it's similar to Docker, but it's using Linux container. And let's say I want to set up a network with 10 hosts and a 5 switch. So the 10 hosts are being set up by the Linux container. And the 5 switch are using the Open vSwitch that is a module within the Mininet. And meanwhile, you can run SDN controller and SDN controller applications on top of the Mininet. So Mininet is the easiest and handy way that one can use for testing. On the other side, we also have SDN equipment like SDN switch from Pika 8 for evaluation purpose.
That is the question of, do you see any feasibility of industry even trying to experiment transitioning from traditional grid to SDN-based grid, or this is more like a conceptual thing for us to do research thing? It looks like there's a question on that over.
Yes, I mean, that's a very good question. So I see the progress. The progress is not as fast as I expected. Company like SEL, Switzer Engineering Laboratory, they have developed the so-called OT-SDN devices. So they have developed the Ethernet switches that utilize SDN, and also the application. I may be wrong with the name. I think like called something like control flow. A flow controller to visualize the flows go through SDN. So they have the hardware that is being developed, and I think right now it has at least go through like 3 generations. The latest model, I like we just had one. Chris just bought one in the lab, and also with the controller level flow visualizer. So that is the closest product, the real product that I have seen in the SDN space applied to the OT network. And I know that there's a couple of ongoing projects within the national lab, such as the Sandia National Lab has OT SDN projects is try to integrate the SDN switches into the OT networks.
Sounds good. I think those are some questions that I thought maybe I see here, but thank you. I think we're going to, I think we need to chat another meeting to just discuss some possible ways that we can talk what we both do and maybe find ways to chat. But this is a great, thank you for your time, Dr. Jen, for your presentation. I think you will receive a nice UND plaque and a certificate signed by our dean, and thank you so much for today's time and your effort. But I think can we schedule some Zoom meeting for 30 minutes at some point next week or whenever you have time? So
yeah, sure. Next week or the week after next, that would be great. I mean, also to know more about your labs, your work. Sounds like at least we can transfer data between the 2 labs, right? sharing data between the two labs, and maybe we can have live transmission between the two test bed.
We have some DOE funding that's already in place. We are already doing several projects. I think I want to just talk, and maybe you're also doing a lot of other related work, maybe that can help in sharing things to each other. Yeah, that's great.
Of course. Yeah, I'm happy to talk.
Thank you. Bye.
Thank you. Yeah, bye.